Before we get to the presentation, I'm going to just provide a little bit of background on the councils. The CTS councils provide opportunities for transportation professionals and researchers to share information on current transportation issues and trends. They bring together university faculty and staff with public and private sector agencies to recommend direction and participate in improving the center's research, education, and engagement programs. I would also like to share that Gina Bass, Samhan Duval, and James DeSoto from CTS are with us today, helping to support the event. Sam will share a link to the council information in the chat shortly. At this time, I'm going to turn it over to our Vice Chair, Beth Ingham, who is co-facilitating the webinar, and we'll go through some housekeeping slides.
Thank you, Christy. So I just wanted to let everyone know that we're looking forward to your participation with questions and answers. And we'd like you at any time to put those in the chat. Otherwise, toward the end, we're going to take questions and you can raise your hand and we'll unmute you in order for you to speak your question. Just also want to remind folks that this event meets the requirements for continuing education credits. So if you would like 1.5 professional development hours or 1.5 American Institute of Certified Planner credits, just send a message in the chat with your name and your email, and we'll get an email out to you with the form. Also check out the CT website for other transportation webinars that are happening this spring. There's a few other ones. And then finally, students, if you are in the audience today, please put your name in the chat because we like to track students who are engaging in our events. So I'm going to turn it back over to Christy and we'll get started with our presentations.
Thanks, Beth. I'll just briefly introduce the presentation and speakers. So the webinar today is going to explore the use of autonomous technology to support worker safety and transportation maintenance operations. We've got 2 presentations today. The first one will highlight a U of M research project that developed 2 low-cost modular transportable mobile robot platforms for pavement density profile testing. The second presentation will highlight a MnDOT effort piloting automated technology in vehicle equipped with truck-mounted attenuators, really focused on safety of our workers. With that, I'm pleased to welcome today's speakers. We have Nikos Papanikolaopoulos, who is a professor with the Department of Computer Science and Engineering, the director of the Minnesota Robotic Institute, and a faculty member of the Artificial Intelligence and Robotic Vision Laboratory. And then we have Ted Morris, a research engineer with the Minnesota Robotics Institute and the Center for Distributed Robotics. And Adam Wellner, he is a lead project manager with the MnDOT Office of Connected and Automated Vehicles. With that, I will turn it over to Ted and Nikos for the first presentation.
Thank you. Good afternoon, everybody. I would like to say a few words before Ted talks about the project. It was a very exciting effort. And I would like to thank MnDOT, especially Kyle, who was the visionary, the program manager, the supervisor, and the enabler for this effort. Also, Dai and Jeff and Mercedes, who really made sure that we were on path. And as Ted will describe the different stages and the design effort and the implementation effort that went into this project. I want to tell you that this effort would not have been possible without the support of CTS and also with the support from the NSF, the Industry Rose Hub Center. This is a center that supports interactions between university researchers and practitioners in order to translate algorithms and technology from the university to use cases. So a big thank you for MnDOT a big thank you to CTS and a big thank you to Ted, who has been the heart and basically the person behind this effort. So Ted, why don't you go into the details?
Okay, thanks, Nikos. So I'm going to share my screen. I assume everyone can see this, right? Okay, so today I'm going to talk about our transportable autonomous robots for assessing pavement quality assurance and worker traffic safety. So just quickly, a quick synopsis. I'll talk a little bit about the background to give some context of why this was viewed as an important effort to accomplish and work on. And I'll go over some of the technology and robot architecture, not in excruciating detail today. I'll mention the full report if you want to, for those that want to delve into more of the real details, a few experimental results that I'll talk about, and just our general conclusions and recommendations. So this is many of our roads in Minnesota are sort of becoming obsolete. That is, their life cycle is such that a lot of these pavements are going to need to be restored or completely a new reconstruction. And this is on top of other new construction projects that are taking place. And the cost to motorists, taxpayers is very significant. So the point being that MnDOT and other agencies want to make sure they're doing it right to get the maximum life cycle from new and restored roadways. So just quickly, a lot of roads, of course, the life cycles related to traffic loads, weather, these kinds of factors. But besides that, and one overriding factor is the fact that the pavement life itself is very much dependent on how the asphalt, and we're talking about flexible asphalt here today, is actually applied. That is, asphalt that has too much air voids in it really degrades if it goes beyond a certain point, and this is very sensitive life cycle. A certain point, it really degrades how long a road is going to last. And there's empirical information that has looked at this over the years. And then if it's too dense, that is, there's not enough air voids, then you get a problem where it starts to shear and you have rutting and heaving. So that's also bad. So there's a sweet spot in between there that construction workers, when they put down new pavement, that you want to be in at all times. So the issue then becomes, if there's a way that this can be measured, and it can be measured during construction, then this information, this data informs the contractors working on the roads to maybe do some other measures to correct and mitigate any problems. Now, there's not time to go into all the various kinds of non-intrusive testing technology, that is, where pavements aren't disturbed. But one prevalent sensor that is becoming much more recognized these days is ground penetrating radar, which has been used extensively in the geosciences and for a lot of other tasks. agriculture. I mean, the list goes on and on. It's a very interesting type of sensor. But for here, we're just talking again about flexible pavements. And the concept here is that with the physics of all this, by just measuring a reflected return of an electromagnetic pulse, a radar, and measuring the return, sort of a peak value, what you get in the return off of a surface of a given material, you can actually obtain a dielectric constant. So just think of that as a kind of like a capacitor, in the middle, the material in the middle, and sort of there's an ability to store charge and let charge go through. That's all I'm going to say about the physics. Is a whole nother topic on this, but that's the point. Is that a properly tuned sensor, just by measuring the signal coming off the roadway, you can actually infer a dielectric constant. Now that constant, and I'm not going to go into all the details here, but the general idea is a lower dielectric constant corresponds to more air voids. Air has a value of about 1, and then as it gets denser and denser, and it's not linear relationship, but just generally the denser pavement gets, the higher the dielectric. So you can use this information by continually going over the roadway by just simply passing this dielectric sensor over the roadway. And one really important piece of information, I should just mention this, is that it can be used on fresh pavement. So this is before you can be driving heavier vehicles and such on it to do any kind of similar inference or measurements. So that's another reason it's becoming a popular method. So the other side of the coin of this is that, assuming this proliferates, which I think many hope it does, is that it can expose workers to traffic safety, traffic problems. So I remember when I worked with some of the MnDOT team here that I was constantly reminded to, the term is keep your head on a swivel. And I did have work zone training, and that wasn't emphasized enough, to really look where, make sure you're really aware of the situation around you. And that very much includes construction and, private vehicle traffic that you might be working really close to. I don't have any more recent data on worker fatalities. I consider one, I think we all do, one as too many. So what we did then is implement a kind of an open architecture robot that can be used for testing this idea of autonomously collecting this information. So in our consideration, one of the requirements, it's emphasized not use any kind of robot that mars new pavement, of course, that doesn't damage anything. And that's relatively simple to configure and cost effective. I'll just mention really briefly, it's a fairly simple way to control this. And the other thing is, these kinds of designs, you can carry really heavy payloads. And of course, you have to balance things. The other side of the coin with this is a non-holonomic type of robot. That is, you can't control where it's pointing and its position instantaneously and independent of each other. But nevertheless, the advantages we feel outweigh the other possible downsides to this. And what you're seeing in the video again is robot doing similar tasks to what the manual a person on the left that's being trained to use the cart system. And then on the top, I'll go into more of this later, but it's having to track actual joint lines at a construction site. So I swear this is the last equation, nothing more than this for the rest of the talk. I just wanted to mention unit cycle control for those of you that don't know. It's just very simply to control your angle. It's just simply the difference of the speed of the left wheel and the right wheel, and then the speed of the robot. Moving forward is just the actually an average, I should say, R/2, an average of the left and the right wheel speed or displacement. And in any event, this goes through simple PID control, and you get the output set points of the left and right wheel speeds, what you want to do. There's things that are a little more involved in doing the actual traversals and multi-path traversals, but again, I'll leave the link for the final report. So the payload, the different kinds of sensors we put on, of course, there's the GPR sensors from the PAVE scan and the rest of the payload that controls all the radars. There's a Trimble GPS receiver that does differential correction, which the MnDOT crew also uses as part of input to their PAVE scan system for getting precise locations. There's also a DME that's a distance measurement encoder that's placed on the wheel that's used in PAVE scan and other similar systems. Typically, they measure a distance along from a starting station number, that's a starting point, to an ending station number. And they also, in this particular case, they use the signal to kind of regulate the rate of data collection based on estimating a speed or a displacement of the cart. So that was just translated onto this robot. And the other sensors you see have to do with camera, long wave infrared camera sensor. These are fairly low cost sensors as compared to the PAVE scan system. Well, they're just low cost. They're $100, $200 kind of sensors. 9 degree of freedom IMU, and this mast is removable, so you can roll the robot into the back of a trunk of a car, which I did frequently to go to different sites to test it. Again, this just shows, I just wanted to point out that the other pieces of equipment for the PAVE scanner mounted on top of the robot. And the thing at the left is very interesting. If one forgets a calibration plate, this is really clever. I didn't think of this. This was a MnDOT people that thought of this one, but you just pointed at the metal reflective material at the right distance, and it kind of does the same thing. So the input of this, when you work with this, is you give it a starting station and an end distance station reference. And as mentioned before in the earlier slide, you noticed, I should just point it out quickly, on the right side is the station number. This is actually a very subtle but important piece of information, as the PAVE scan uses a different kind of reference where the sensors are as compared to the stationing of where the robot thinks it is. So you account for those things. And then you also input a CAD file of the roadway. So that information gives you alignment information for different kinds of curvatures and horizontal straight sections, that kind of, if you will, macro definitions, which can be translated into a full path for the robot to reference. And then you enter in the number of traversals going back and forth, how far those offsets are from known reference center line, for example, or shoulder, number of times you do this, go back and forth, how fast you want to move the robot, typically walking speed, and then you must also do a calibration procedure of the GPR itself, and configuring the starting and ending station reference numbers, using kind of that diagram up above there for deciding offset convention. So our first experimental field testing, amongst other places, was at MnDOT. The geometry and the characteristics of pavement are well studied and well known, being that's one of the purposes of the MnDOT facility. And so we also did some testing at a construction site. In our case, the selection has to be very limited to isolating us from any private vehicle traffic in this case. So first, just some quick results. One set of results is just moving forward and back amongst different traversal paths. The endpoints, part of that is the recording of points as you transition from one traversal path to another, where the offset. But generally, the offsets are the following errors between about plus and minus 4 inches. And then collecting GPR data, some of this, we're only looking at data within that plus or minus 4 inches. But it kind of makes sense. On the bottom, so as you look on the midline at the bottom, which has a higher dielectric, meaning it's more dense, and on the joint line, which has near the joint line, which is a lower dielectric, meaning it's less dense, that there infers there's more air void in the pavement. So one of the things we did, besides doing the latter types of experiments with in situ joint detection and tracking. That is, when you get a drawing or your CAD information of where road center lines, lanes, and so on are supposed to be, question is, are they actually located where they're supposed to be? That being, you would ideally like, for example, center line to be located in the middle of the roadway to avoid any vehicles driving over it, repetitive loads going over that. And also, it could be used as a record for future construction work to kind of give a modified joint line if necessary. This is all done just some very relatively basic computer vision steps with the limited data. This is one way to do it. This is a very efficient algorithm that can run on very simple, low-cost processors. And the idea is you then just localize where estimate of the center line is using the camera, IR camera, to differentiate temperature, because newer pavement is a lot warmer than pavement that was laid before it. Ideally, you drive the robot about, I don't know, 1,000 feet or so back from the last roller pass, for example, on top of the pavement, and then you measure infer the asphalt pavement density along different joints, whether they're constrained or unconstrained. And what you're seeing there is the image from as the robot's moving along a unconstrained joint. And you can see the temperature difference between, well, it's very obvious here between the ground and the pavement. So in this regard, we did some tests, a kind of repeatability tests between going traversing down one direction, coming back the other, and looking at the offsets from the center line on two areas. One that was, this is County State Highway 92 and Highway 12 out west. Was back in 2022. Wow, it's really has been that long. So yeah, and it's just showing the areas where we did some testing. So here's what we got, and this is kind of interesting. Along the straight section, one of the straight sections, it was off a little bit, by roughly a half a foot or so. There were some other verification things we did to know if this was to verify the accuracy of this and the variability. The second one is very interesting, is much more dramatic. It was off considerably. I don't know if this is maybe atypical of construction jobs. Actually, I admit I really don't know. We'd have to do more studies. But the point being that the center line where it was actually built is considerably different than where the joint line is. And so where this is relevant again is that vehicles could likely be driving over where these center lines are, and it can affect perhaps the pavement life. I don't have time to show videos again. I do have the videos of this data output, and I can share that with people if they really want to see it. And finally, the other piece is basic object and collision detection. Now, the action of the robots, there isn't really any path planning for this. It just the action is to decide how to stop and pause the robot. It doesn't try and maneuver its way around things. It just identifies where objects are in a given envelope of the GPR system, the arms going off to the side, and then up and down if there's an obstruction on the roadway. Again, there's just more explanation in the report, but this is just the general idea. It turned out, the best sensor in our case with the hardware we had was a Z camera, and extracting the perceptual data from that. So just a few concluding remarks. We at least developed a couple robots. There's actually two of them to be able to test and assess this type of method. Again, we can track the pavement joints, either they're constrained or unconstrained. And I'm not really sure if this is an outlier. Maybe it's really not all this, it's off as much. Actually, there are some other data which it was only a few inches off that I didn't show. But I think the future work, and this was something we had originally wanted to plan, is to modify the robot path traversal to use these center line, average these center line locations in front of the robot instead of the design ones. And of course, to continue to improve the traversal accuracy with further tuning. There's a lot of different parameters the operator can play with, though. Our report suggested one set, but of course you can do other experiment with other parameters. The other, I would say, a shortcoming with what we're doing now is the system that was deployed. It's a closed and proprietary architecture. So the ideal integration with the robot architecture, using the displacement information of the robot, being able to actually have the robot give, the sensors give information not only to workers, but perhaps the robot itself to, slow down or go over certain salient areas that might be problems. And the other side of doing that is to make it a much more usable system. There's a lot of kind of dual effort, so to speak, in configuring the robot so it is similarly is matching the information on the PAVE scan system. And so I think that's all I have, and I'm not sure if there's questions now or if that's later. And I want to mention, of course, big shout out again, Nico's already said it, but without the support of MnDOT, it wouldn't have happened. There and just a really patient team that were incredibly helpful in shaping ideas, requirements, really keeping it grounded in reality. So I really want to give special thanks to them. And that's it for now.
Thank you, Ted.
Yeah.
I don't see any questions, clarifying questions at this point, so we'll plan to take questions after
Okay.
Adam goes through his presentation.
Sure.
So Adam, if you want to get started.
Yeah, just let me find the right thing. Okay, looks like the right one's up. All right. Well, thank you for giving me the opportunity to present. I'm with MnDOT's Office of Connected Automated Vehicles. And just to start, I always like to start presentations like this with some level setting. I deal with a lot of different audiences. And so just to make sure everybody's kind of understands where we're coming from. So MnDOT, CAVX, CAV, this is some terminology that gets thrown around a lot, but a lot of people don't necessarily understand exactly what all that is. And so CAVX is MnDOT's Office of Connected and Automated Vehicles. It's a group within MnDOT whose purpose is to look out for how automation is going to affect the way MnDOT does business, whether that's with automation in MnDOT's business or how automation and connectivity change the way we need to do business as the fleet of vehicles that private citizens own driving on our highways gets to be more and more prevalent. And we talk about connected vehicles, which is any sort of vehicle that communicates with other vehicles or infrastructure. And then automated vehicles is any kind of self-driving vehicle, which would include things like driver assistance features, adaptive cruise control, lane keeping, automatic emergency braking, those kinds of systems. So it's a pretty broad definition for automated vehicles. Today, I'm specifically here to talk about a project that we have been working on with some MnDOT equipment, which is the Automated Truck Mounted Attenuator Project, or ATMA. The ATMA, it's an automated vehicle or self-driving, and it's a host vehicle for a truck-mounted attenuator, which is a device that is attached or towed by a truck. And when we talk truck, we're talking, in this case, like a plow truck. It needs to be a large commercial vehicle with the weight. They're used to absorb the energy of a crash and protect our work crews when we're out doing maintenance work. If someone's not paying attention, instead of them hitting our staff, our work crew, and our equipment, they hit this attenuator and it absorbs the energy, hopefully preventing injuries and fatalities and impacts to our work crew. And they are really good at absorbing that energy and reducing the risk to those crashes. However, there's still a hazard to our workers because we have to have someone in that vehicle driving that vehicle today. And just kind of give some more context like what that is. So this picture here is the cover of Minnesota's temporary traffic control field manual, which is the guiding document for traffic control on all roads in Minnesota. And you can see in this picture, a great picture, we have one of these attenuators. It's this yellow thing on the back of this plow truck behind the aero board. So if someone were to hit that, the energy would be absorbed. And here's an example of how we would use this in practice for anyone who isn't real familiar with this. When we are doing a lot of our shorter duration maintenance work, patching potholes or guardrail fixes that are shorter duration, we typically, instead of taking the hazard of having to set cones and place a longer term static closure with an aero board, we will actually use trucks to establish that closure. And so we'll use a series of 3 trucks with aero boards and these attenuators mounted on them to create a lane closure to protect our work crew who's performing work on the highway. And this is an operation that MnDOT crews do regularly with human operators. And our objective is to get some of the people out of those vehicles. So if somebody hits them, we don't have a person sitting in that seat. So the ATMA right now, as it sits, we have a pair of trucks set up with a leader truck and a follower truck. The leader truck, which would be the first truck in that string of 3 trucks on the picture I previously showed, is driven manually by a person sitting in that truck normally. The follower truck, the next truck back, which sits halfway in the lane, and would be the first truck into the lane that someone would encounter, with the ATMA system, automatically follows the leader truck with an offset, or whatever parameters we may give it for its following. And like I said, the objective here is to remove our operators from potential harm. With the asterisks, we're not there yet. We're not at a point that we're ready to pull an operator out of that vehicle. There's legislative challenges, but quite honestly, as an engineer, I'm not comfortable enough with the system yet. That's why we're doing this, to build that comfort, to remove that operator. But we got to start someplace. So here's a couple of pictures of our trucks. They look, if you're not paying attention, it looks a lot like just about any other MnDOT truck. Our leader truck is just a standard plow truck with just this antenna rack added to the top. And the follower truck from the outside looks pretty similar, except we've got this suite of sensors on the front, which help with some object detection and some blind spot detection. As this truck is being operated from the leader truck, we need a little more information about what's happening around that follower truck. So here's a couple of photos of inside the leader truck, and I'm not, these are not all our vehicles. Some of these are from a couple other states. We are one of several states which have been experimenting with this technology. But inside the cab, we have a couple of boxes that control emergency stop systems, that if the operator hits this big red button, everything stops. The follow truck, the engine stops, the emergency parking brake is applied, and that truck isn't going anywhere until we clear that error. And then additionally, this stuff here is plow related stuff, but this here is a tablet where they can control how that follow truck is following them, how far back it is, and then how far left or right it is, as well as set up the system to run. And then there's also some cameras so that they can get a little better view of what's happening with that follow truck. The follower truck it has some additional hardware installed. It's also got the emergency stop buttons and some controls in there, but it also has equipment to actually control the vehicle. The system here has no direct integration with the vehicle electronic systems. The steering is done with a steering ring that is bolted around the steering wheel, and it's got these fingers that stick up and just interface with the wheel and literally turn the wheel. From the truck's perspective, it doesn't know that it's being driven automatically. And then similarly, there's some actuators on the brake and accelerator pedals that will pull them to drive the vehicle and apply the brake and accelerator. And otherwise, if we have the system off, the truck can just be driven by a person in the driver's seat normally. So here I have a short video from one of our yards of the two trucks, and you can kind of see how they follow. So we got the leader truck coming along, and there is no sound. And the follow truck's coming along, and it will follow that same path that the leader truck took, taking that turn. Essentially following like a breadcrumb trail is how it's been described, that the leader truck leaves for the follow truck. I will say the system is extremely accurate. I was out with the crew while they were supporting some pavement marking striping operations, and we had to pull over to the side of the road to let traffic by through wet paint. And there was one set of tire tracks through the paint. The follow truck followed. You would not have been able to distinguish the difference in the tire tracks between the two vehicles. It was one set of tracks through the paint. Okay, so I'm going to talk a little bit now about how we got here, some of the history of the project, and then kind of where we're intending to go. So this system, MnDOT didn't develop this system. It was acquired through something called the CAV Challenge, which is an open RFP that MnDOT has for innovative ideas like this. MnDOT selected this project and worked with a vendor to get the system installed on a couple of MnDOT trucks. So the trucks were sent to the vendor to have the system installed. After the system was installed, there was some closed track testing that was performed. I believe it was done at the Elko Speedway. Just to let's get some comfort, let's do some training. And then the first 2 years of the project, the trucks were placed in the Lakeville truck station in the metro as a tool for them to use when they're doing their work. We learned some things through that process. Not all of them were great successful things. Actually, I would argue many of them weren't, but we learned, and that's our objective here. So we had some issues in the metro that appear to be GPS issues. I'm not actually, based on some things we learned late last season, I'm not sure they actually are GPS issues. And it was more of a problem that was happening at the same time the GPS was trying to lock. So it was showing up like a GPS lock, but I don't think it actually was in hindsight. I think we found the problem there. But we were being told we were having GPS issues in the metro with the tall buildings. That's something we're going to have to work through because we do a lot of work in the metro. Anytime we had a failure of the system, which we're still experimental here, the trucks would need to get out of position. We couldn't be protecting that work crew while we restarted the system. We also just unfortunately had a series of unrelated equipment failures. Things like transmission intercooler failure that shut down a truck for 2 months because it needed, parts replaced and parts were back order and we were getting coolant in the engine oil. These things happen. This is the reality of working with vehicles, and we have a lot of equipment that breaks down. It just happens. Then when we got back on the road, the equipment that they were attempting to use with this closure to actually perform the work broke down. So there were some challenges getting on the road. We also discovered that steering ring that goes behind the steering wheel blocks the dashboard, the visibility of the dashboard more than I think anyone really expected. And there was actually an issue where there was a warning for a diesel particulate filter regeneration that went on, which isn't an emergency warning, but if you don't take care of it in a certain amount of time, the truck will go into a parked regen and it'll just sit there and you have to leave it parked for an extended period of time. while the truck regenerates its diesel particulate filter. And that's basically enough time to pull it to the side of the road, and that's about it. So the truck had to sit there and wouldn't go anywhere for a while until that got resolved. And so we learned, hey, we need to be able to see the dashboard a little better than we are. That's something we honestly probably should have caught earlier, but we realized that was an issue. And a lot of those things all combined to the first couple of years, we had limited hours of testing. Additionally, it didn't help matters that the contract was signed, I believe, in 2019. So we also had COVID in here slowing things down just across the board. So then in late 22 is about when I joined the office, and in 23 we took a little different approach. So we took some of this operator feedback we were getting and said, hey, went to our vendor, said, hey, we need to see some changes here. So we implemented some software changes to address MnDOT needs. The biggest one is the ability, if we have a problem, that we can start the trucks, start the system from where the trucks were when the failure happened, if we're offset. So we may have to have the crew hang on for a couple minutes, but we don't have to clear off the road in order to get the system to run again. This isn't hopefully something we need long-term, but as we're in development, we need to think about those things. Because if we're just running manually for the entire day, we're not gaining anything if we can't get the system back online. Also, we learned a few things about the way that equipment was attached to the trucks. It worked, but it really didn't hold up to the plow truck environment. Anybody who's been in a plow truck, or hasn't been in a plow truck, they bounce around a lot. It is definitely not a friendly environment for any kind of equipment. And we were losing bolts and nuts due to vibration, even when they had Loctite on them. Things just, they worked their way loose. And so we rebuilt basically all of the hardware. So that, the pictures I showed were the rebuild that our MnDOT mechanics performed. Additionally, the use of integrating this into the MnDOT, just into a MnDOT truck station, honestly didn't really work. Their job is to do maintenance in Lakeville, and they didn't really have the time to dedicate to fixing problems when they occurred. And we're in research and development. We have problems, like we acknowledge that. So we took a little different approach. We've hired some staff on board to this first year we tried it. We hired 2 people temporarily into our office that worked directly with me to do testing. And then we said, well, let's try to get out of the metro and try some other areas. And so these 2 guys traveled around the state, visited all 8 of our districts within MnDOT to support testing. And then this also gave crews an opportunity to see the system other than the people in Lakeville. And so it was a little bit of an engagement opportunity as well. We did have a little bit of a slow start. We had some bugs to work out. The system had sat for a couple of years without a ton of successful operation. We had to get those things fixed, any of the things that had vibrated loose and such. So it took us honestly till about July to get really on the road. Once we got those bugs out, we had a lot better luck. And in the first 2 years, we got about 10 hours of testing, and last year we got probably close to 400. So we saw some significant improvements in the amount of time we were able to get on the road to learn some things. So what did we learn? We learned some more great things that weren't necessarily the things we went out to learn, but that's kind of how this project is set up. One of the things we figured out is we need to pay attention to how all of the equipment on our vehicles interacts. We have a lot of stuff on these trucks. And we were having a weird problem anytime we changed the message on our aero board. Well, we did some research and found out that the controller for our aero boards happens to use the same frequency band as the equipment the vendor provided to connect these 2 trucks. And so it looks like we were probably getting some interference there. And we've learned we can kind of cycle the frequency that aero board uses and kind of push it to a little different area of the band it allows. It's a little bit of a trial error. You just got to kind of repair it a bunch of times until it works. But that seems to have helped, but we have a lot of radios and things like that in those trucks as well. So that's something we need to think about as we are deploying stuff in the field in our trucks. We learned some things about our crew integration and planning, and just generally like how our crews, when we're working with the automated vehicles, some things take a little longer than if we're normally used to when we're pulling out into the road. We learned we need to communicate those things, and we've learned what we need to communicate a little better. And just little minor changes that need to happen to the way the crew actually performs the work or gets started for the day. Nothing that would really change the end objective, which is getting the work done. But in some ways, we need to communicate and plan with those crews in order to do this. We gained a lot of internal knowledge about how to troubleshoot the system and how to work with it. And that was, I think, a significant success from a MnDOT institutional knowledge perspective. We had an interesting issue with tall grass. So oftentimes you get into the later fall, we get some grass growing up through our joint between the mainline pavement and the shoulders, which is oftentimes an area we're running one of these trucks. And the forward-facing LiDAR sensor on the trucks was detecting that tall grass as an obstacle, and rightfully so, not wanting to drive through that tall grass. So we do need to be cognizant, I guess, of the environment we're going to be working in. And we just didn't even think about the fact that grass might show up as something that you can't drive over. It takes a long time to change lanes, or can take time to change lanes, differently than with a normal human-driven crew. And additionally, bridges and other overhead obstructions can cause a loss of GPS. There is an inertial navigation system, but if we stop under a bridge, we're going to have trouble. So our crew can adjust some of our spacings a little bit to try to avoid either vehicle being under a bridge for an extended period of time. We also very much established that this MnDOT dedicated crew was really the right thing to do for a research project. The operation of the system is honestly not that complicated, but the fact this is research, there are problems we are facing. MnDOT learned we need to, if we're going to do these things, we need to dedicate some staff and build some skill. And I think give that person in the field, empower them to fix issues, and not everything needs to come up through managers and supervisors in order to get something solved. Let them call the people that can fix the problem. And actually, so much so that we have actually one of the people on the crew we hired full-time into our office to support this kind of work. So moving on, we're into 2024. I'm actually going to go to the second bullet first. We are continuing statewide testing. Monday was actually our first day back on the road. So these trucks are out there. The crew is actually out there today, doing some, I think they're out patching today. And we're going to continue to learn what we can, and hopefully we can get a good solid year of success. And hopefully we have less issues than we had last year. And that's kind of the objective, is to just have less problems, see what we can learn. We're not ready for widespread deployment yet, but we're trying to learn the things so we can get towards that point. Additionally, one other thing MnDOT intends to do this year in the fall is we're going to hold a design workshop, kind of changing the approach as to how we would do this kind of work in the future. The system we had right now is very bolted onto the existing truck. It's very apparent if you see it, that it is very bolted onto the truck. MnDOT's in a unique situation, at least compared to, I'm assuming, many agencies on this call, that we actually build our own plow trucks at a MnDOT shop. We buy a truck chassis, and we put all the equipment on there ourselves, or with some contract support. And so we're in a unique opportunity that we have pretty much a bare truck at some point. And so my belief is if we do another truck, we're going to build that up through our plow build and get everything incorporated there. So we just a little more streamlined, a little more integrated, where we have a chance to put things like in frame rails and stuff like that before it gets covered up in a lot harder to work. So that's kind of where we sit today. I guess I'm open to any clarifying questions. Otherwise, I can hand it back, and I think we were ready for bigger questions.
Thank you, Adam. We'll take questions now for both of the presentations. You can go ahead and raise your hand if you'd like to be unmuted. Otherwise, we do have, I think it's one question here in the chat, and this would be for our first speaker. What ASIL does the system have on the truck controller, ASIL? Ted?
Oh, hi, I'm sorry, I was muted. Can you repeat the last part? I'm sorry. My audio is.
What? On the truck controller, what
Yeah.
ASIL does the system have?
On the truck controller, is this intended for me?
Yeah, it was a question that popped up during your presentation from David.
Oh, okay, on the
Sullivan.
robot. So it uses closed loop speed control rather than torque control. I don't know if that answers the question. Internally, that's uses a PID type of controller in speed control to regulate current. And there's again, it's a it's an open type of controller for brush servo motors. I'm not sure if that answers the question, but.
So David put in the chat again, a couple more. I don't know. He says not the robot, not the
Yeah.
robot.
I think he may have been intending
ahead.
that question for me. I will be honest, I don't know a whole lot about the control system on the truck. This is purchased from a vendor who is very, very closed with their intellectual property. So like we know a little bit about the hardware, but we don't know a lot about the control systems themselves, unfortunately. I hope that actually answers the question.
Thank you, Adam, for clarifying. Sorry, Ted.
No worries, no worries. People got some more free information.
Does anyone else have any questions for our presenters here today? Feel free to raise your hand if you'd like to be unmuted. Otherwise, you can type your question in the chat. We'll get it out.
I had a question for Ted. So it sounded like a lot of the application you guys were looking at was probably to use as pavement is being constructed, like for the
Yes.
testing for the compaction. Do you anticipate this being used by geotech consultants as well to do ground penetrating radar? Because I know we hire them a lot to look at if we're able to rehab a pavement, and a lot of times that's part of the scope. So I'm just kind of curious if the vision is to have that expanded to that area as well.
Well, yeah, internally, we talked about, what about in terms of the type of GPR it is in measuring just compaction type of information, but certainly can be evaluate as built roads. I believe there are a few other kinds of issues associated with that, but in that regard, as far as other types of evaluations, such as forming potholes and things like that. I don't know if that's something that you're inferring. There's different kinds of GPR technology. It's not quite like this one. There's a way of you can kind of basically you're reconstructing an echolation image. It's called a B scan, and you can actually obtain profiles of larger voids that are occurring below grade, below the pavement surface. It's a very interesting application, and it would be very interesting to adapt the platform for that.
Thank you.
Sure.
So Adam, I had a question for you too. I was kind of curious, you mentioned at some point you'd like to deploy, have a wider spread deployment for the trucks. And I'm just kind of curious, like what steps do you see being needed in that process? I assume there's like legal and safety groups that have to weigh in. I'm just kind of curious if you guys have thought about that.
Yeah, so I mean, there's a couple of things, and one of them is we need to get the system something a little more robust, maintainable, stable, admittedly, where we're not having to spend near as much time repairing it. Like I said, we're okay. It's research, but I don't want to hand that over to a lot more crews if we're having problems that we need to chase down. And then that like the design workshop that we're holding to really understand how we can integrate it a little more cleanly into a truck. And so that's really the first thing is we just need to build some confidence and understand that, yeah, we can do this. And this is what it's going to take. And if we need to make any other modifications to the hardware or software, there are definitely some other software things that we need to implement just to make it practical from our side. Like right now, our leader truck and our follow truck it's those trucks. It has to be that pair of trucks, and they have to be in that setting. The leader truck has to be the leader, the follower has to be the follower. That doesn't really work from a large scale fleet management perspective. We need to be able to mix and match trucks because you get intercooler leaks and things like that. They happen. You need to be able to swap out vehicles, otherwise you're shut down. So we have some of those things that we need to push development on to get those integrated. And once we're in a little better spot there, then yeah, we would need some legislation probably would need some legislation. Our lawyers haven't exactly chimed in on that, but probably need some legislation allowing us to have a vehicle without an operator in it. We would always, or we intend to always have an operator drive the vehicle to site, but then that operator be able to get out and move to a safer location within the site. That's a number of years down the road. We don't want to jump towards legislation until we're comfortable on a technical perspective, though, because likely that legislation wouldn't just apply to us; it might apply to others. We're very conservative when it comes to safety.
Absolutely. Are you guys also trying to test it in different weather conditions too?
We would like to try doing some snow and ice support this winter. Weather, I mean, sure, we would do it in other weather, but the reality is we're not out doing a lot of maintenance with lane closures in poor weather. Like we have no problem with being out in the weather, but you can't patch in the rain. Like this just doesn't work. You can only do so much mowing in the rain because you have other problems with doing that work. But we are going to try this winter doing things like when they're clearing around guardrail and some other work like that, where we had to haul snow, doing that sort of operation this winter.
Thank you.
There is one question in the chat that was a follow-up from Christy's first question about GPR. And the question is, sorry about that. What's the maximum speed of the robot platform that can produce usable GPR data?
So the platform can, the maximum speed is a little over 5 miles per hour. Generally, so it's kind of also a question of the pave scan systems. There's not being a big, a really highly trained user of pave scan, but I believe you can set different speed modes of the GPR, to sort of between driving and walking. And then it's a bit of a long answer. I'm always long-winded, but then in turn it can regulate the acquisition rate of the pulses, that it directs down at the pavement. So in that regard, these systems have been, deployed on vehicles too, going at essentially nearly highway speeds, roadway speeds.
Thank you, Ted.
Sure.
So one last call for questions. If you want to type it or raise your hand and we can unmute you. All right, well, seeing none, I guess we'd like to say thank you both for your presentations. And then Christy,
Thank-
are we on for round robin?
Yeah, we can quick check if anybody wants to share any information about any issues your agency is facing or events that you'd like to share with the group. Feel free to raise your hand and we can unmute you or put it in the chat and I can read it for the group. Or if you have any ideas on future council research topics or presentations. I think Sam put the questions in the chat. I'll maybe give you all a minute. Well, it seems like we have a quiet group today, so not seeing anybody raising your hands or providing any information. We will close out, and I just wanted to thank you all for joining us this afternoon for our presentations, and a special thank you to our presenters, Ted and Adam, and Nikos for sharing their research. Have a nice afternoon.
You as well.
Thank
Bye.
you.
Yeah,
Thank you.
thanks
Bye-bye.
a lot. Bye-bye.